Hi, Anthony Zuppero here. We use the discovery of an electron-catalyzed binding reaction from chemical physics during the last decade as a template to understand LENR. Our model happens to define a nuclear active environment. However, we only claim the initial binding reaction. The discovery from chemical physics places 6 to 12 MeV inside the nucleus, and it's initiated from thermal or even cryogenic initial conditions. Everything else follows from this, including resolving an illusion that the Coulomb repulsion is somehow bypassed. First, we show how to bind nuclei together using a cold heavy electron and modeled like muon-catalyzed fusion. Then we show how to create and use transient heavy electrons in the conducting crystallites, modeled as muon surrogates. We begin by observing that common to all reported LENR, a short wavelength crystal momentum impulse is always inserted picoseconds before transmutation. Finally, we show how the entire LENR dataset appear to support our conjecture. We only claim the initial reaction. The initial reaction energies, this reaction, can energize many theories. Recently, 1999 through about 2011, chemical physics discovered a new binding reaction. An electron with an effective mass above a threshold passes between reactants that are attracted to it more than they are repelled by each other. And, crucially, we choose reactants that are attracted by an additional independent binding potential. Then, prompt binding and energetic electron emission happened. Chemistry and muon-catalyzed fusion. If we substitute nuclear binding for chemical potentials, we get transmutations. You must be familiar with the H2 plus ion. This is quantum chemistry 101, as fundamental to chemists as the simple harmonic oscillator. It defines a momentum repulsion. The total energy includes a Coulomb attraction and an electron momentum repulsion term. That's the basic quantum chemistry, and it scales like inverse mass. The key to the process is to add a binding potential with an effective range smaller than the chemical interturning point. You'll see this forces tunneling. Electron catalysis then becomes a quantum kinetic energy of confinement process. The quantum kinetic energy of confinement is about 200 MeV for a normal electron at nuclear dimensions. Therefore, a negative 6 to 12 MeV binding of protons or deuterons to reactant isotopes that you take from across the entire periodic table is too small to cancel the positive, repulsive 200 MeV. No cold fusion can possibly occur. But if the electron mass is high enough, the quantum kinetic energy of confinement drops to less than the attractive binding and attractive Coulomb energy, the sum of the two, and the ground state dips to just below zero and becomes stable, forms a double potential well system. When this happens, this defines the effective mass threshold. The second potential well at nuclear dimensions has only the ground state stable. It forms when mass exceeds a threshold. So a gamma-like estimate shows that the chemical species can tunnel to a bound species. The bound is a new nucleus or a new molecule. It does so with a small but useful probability. For hydrogen binding to nickel, the probability during the lifetime of the crystal momentum phonon is about 30%, and the mass threshold is about 35. These are reasonable, high but reasonable. For deuterium binding palladium or binding titanium, or about 90% of the isotopes in the periodic table, that's a surprise. It's only about 12 electron masses. Definitely a surprise. We saw a pattern in all the Leonard data we could find back to the late 1800s. Every Leonard has a process that ensures short wavelength crystal momentum impulse into a reaction crystallite in or on which reactants are adjacent to each other. That is our nuclear active environment. Iwamura used absorption on the surface of palladium to inject short wavelength crystal momentum. Many people use glow discharge to insert 100 eV protons or deuterons into the crystallites. Rutskwev and Adamenko over in Russia and Ukraine, they use disintegration of solids to create the impulses. So what does short wavelength mean? 2 pi over lambda, wavelength, it's crystal momentum. In the first Brillouin zone, electrons near an inflection point have elevated effective mass. 1 over curvature. There's 2 points per line per feature in the first Brillouin zone. The boundary represents 1 over crystal unit cell size, the first Brillouin zone, 1 over the crystal unit cell size, 2 pi over it. Augustine was right. He and his colleagues said you cannot use a heavy electron from solid-state physics. Why? The boundary condition for effective mass is non-interacting, ballistic. So here's our justification for using. For limited use, we'll show you limited, of electron quasiparticles. Non-interacting means all forces cancel. The equilibrium position of conduction electrons are where all forces cancel. This means conduction electrons originating in the region of equilibrium are the catalysts. So how can a non-interacting thing be a catalyst? A crystal momentum impulse has spectral components, some of which can overlap inflection points. You hope a crystallite has inflection points near the Fermi level, so the electrons don't also need extra energy. Palladium hydride has at least 2 inflection points near the Fermi level. Titanium hydride has many. The flat part, it's in the white space between the W, the L, the gamma, the X boundaries. The white space may have a zero curvature segment. Note, there's many places where curvature is zero. Nickel hydrides seem to have many accessible inflection points. It seems no matter what crystallite we pick, we find many inflection points. Why do defects make such a difference? Defects, crevices, boundaries, facets on a crystal. Each defect inserts a pair of inflection points. Makes it easier. So now 2 branches clearly appear. Here's how our data fits a theory. When we look at 30 years of Leonard data, we see a binding branch and a fission branch. The binding branch is where hydrogen and deuterium appear to just bind with the reactants. From aluminum through uranium, they just bind. In the fission branch, instead of binding, the nuclei explode. This is where non-interacting and interacting makes a difference. If the heavy electron begins close enough to its equilibrium point, binding occurs, the binding branch. But where did the energy go? We don't know. 6 MeV electrons inside a nucleus suggest electron capture. But when the electron interacts at some point during the Coulomb attraction collapse, it reverts to a normal electron if it didn't start exactly at the equilibrium point. A normal electron can only tunnel to within about 6 to 8 nuclear radii, given the binding energy that we have, 6 to 12 MeV. The electron brings protons and deuterons approximately 6 to 8 nuclear radii, that close. These polarize and deform the target nucleus. The strong polarizations make the nucleus look like a football. It lowers the fission barrier. These energies are greater than the binding energy of alpha particles in the mid to heavy nuclei. When the electrons started heavy, it was closer to nuclei than normal electrons. Just closer is enough. So when it went normal, it was still just close enough. This feeds our postulate for the fission branch process. The binding branch matches theory exactly for chemicals and muon catalyzed fusion. The components bind, the energy goes to electrons. But for transmutations, where does the energy go? We don't know. The transmutation bindings are predicted and observed. Some can be radioactive. Robert Godis and Mike McCubry postulated electron capture. The data seem to confirm some of their conjecture, and that single tunneling that we postulate would energize their conjecture. Our thoroughly contemptuously anti-cold fusion mentor, it's Professor Gabor Somerjai at UC Berkeley. That's where we did the counterpart chemical research to this work. He mandated, follow the data, in a thick Hungarian accent. Okay, the data overwhelms us with pairs. Reasonable, electron pairs. Iwamura began me on this path. Pairs of deuterons, 1, 2, or 3 pairs, appeared to bind with isotopes from calcium to tungsten, the whole damn table. When we use n pairs of reactants and heavy electrons, we can match fission products, apparently accounting for everything seen. You might have to add a McCubry and Godis electron capture to account for everything. So one can nearly always find the isotope resulting from binding n pairs to a reactant in any EDX spectrum of Lehner products. Now notice the hydrogen pair reactants, not deuterium alone. One of the pairs produced yttrium-87, radioactive. The 3.5 day half-life was observed after an electrolysis. Mizuno analyzed the fission products of an experiment that exploded. Hydrogen, not deuterium, and tungsten created isotopes. All the isotopes he saw pair up. Protons and neutrons add up when a pair of hydrogen bind with tungsten. Notice the energies, 60 to 115 MeV. The energy is fission products, stable ones. You'd expect them if it took a long time to assemble them in the nucleus. That's what the Coulomb collapse gives you, a lot of time. Heat is the usual result, excess heat. Froelich of NASA, he published the isotopes they saw on a hydrogen purifier after it purified deuterium. At the part per million level, his isotopes line up as pairs. When one or two pairs of deuterons bind with a lattice palladium, the new nucleus explodes into the isotopes we see. I paired them. Note the energies, about 40 MeV. Pam Mosier-Boss documented the fission products over at Point Loma, the Navy. Every isotope she reported is accounted for except the bromine. The bromine would have boiled away, and its L-alpha EDX signature lies directly under aluminum, so you can't see it. I saved the best for last. D fusion. The energy of D binding with nearly any isotope is about 12 MeV. The binding energy of an alpha particle is negative, which means it comes out all by itself, for heavy elements like uranium, which is an alpha emitter. The binding energy of the alpha becomes positive and less than about 6 MeV for things like calcium and middle of the table. Nickel, palladium. The product of a pair of H's or hydrogen deuterium or a pair of deuterons is cadmium. It's a cadmium nucleus with enough energy inside of it to literally explode it. It explodes into fission product, helium, and the original isotope, like a catalyst. Or it explodes to an isotope of the same element with 2 less neutrons. If you're using hydrogen, you still get helium if you start off with a pair of hydrogens. The only reason you don't see it all the time is it's a higher effective mass required, 35 instead of 12. We postulate helium as a fission product. You might say deuterium and anything, almost anything, produces helium and the almost anything. In conclusion, we only claim the initial reaction that binds a proton or a deuteron to an isotope from a thermal-chemical state. This single claim can energize many theories. Thank you.